Good afternoon, everyone. So today's class, we are going to be looking at the interesting part of this course, which is the AC motors. And before I jump into that, let's just quickly look at the homework aid. It's a very simple homework question, just solving the current in this network. And you can use either method. You can do Laplace or you can do differential equation, find a particular solution, general solution, however you want to do it, either Laplace or the differential. But whatever method you use, this should be the final result that you end up with. So there's a couple of interesting things here. In the rest remaining of this course, the part we are interested is only the section, right? The magnitude and this portion along the steady state current, sinusoidal current, which is basically this diagram here. So we have some voltage and the steady state current is going to look like this with some phase shift given by the tan inverse omega L by R. But in reality, there will be a transient portion as well. So when you set up the circuit in some simulation, this is the response you'll get. There is an exponential term which is decaying, right? And then the sine is basically the peak of the sine is going to create the exponentially decaying waveform. And you have the sine that then settles down at the steady state that we are interested in observing, right? So there's one interesting application to the reason I asked you to do this is because in our course, the remaining, we're only looking at this, but when we go to advanced electric drive, this portion is of very interest to us. Because if we look at the DC motor control that we are doing, the steady state is not what we are trying to shape. Steady state is taken care by the integral term that we had. But we were interested in how the exponential terms evolve. We wanted to have underdamped case or overdamped case. In the homework, when you did 30 phase margin, 45 phase margin, and 60 phase margin, you would have seen for the 30, it was very oscillatory. For the 60 degree or higher, it was very overdamped. Those are all contained in the exponential terms of our equation. So when we do, even in this course, we will do a little bit of control towards the M, D by F control. That again works on the steady state of the electrical circuit. It will still operate on the transient of the mechanical network, but not on the electrical network. It will assume the electrical network has already reached steady state, and then we'll do some control on the mechanical aspect. But if we want to manipulate this transient term, how it behaves as well, then we need to go into something called vector control, which we'll cover in the 5705 course, which will be taught in the fall with the associated lab. But for this course, we'll stick to this. But even outside of this, when you take a power system course, this term is of extremely critical importance in power system analysis because if you look at what the term means, it says, if I want to take out this exponential response, what can I do? When will this exponential not exist? If I have given you this RL circuit, you cannot change this RL parameters. You cannot change this voltage in any way. How can you still eliminate this exponential from ever occurring? Not even in transient. Yeah, Leo.
When the sine term goes to zero, essentially.
Perfect. So when this term goes to zero, that's basically saying your theta equal to 5. You won't have any transient. So what that means is that when I turn on the switch, if the theta is such that, so basically if I turn on the switch at this instant, if this was my t equal to 0, instead of this, if this was my t equal to 0, so the voltage will start with some magnitude, and at steady state, that magnitude would correspond to 0 current, right? If I time the switch perfectly such that the voltage is at this particular value for the given network, will change with the network what that value is, because this phi is tan inverse omega L by R, is a function of the network parameter. Then I can make sure the current will start at 0. And if I were to give you this waveform, there is no way you can tell whether this is a transient evolution or a steady state evolution. Because even in the steady state circuit, for this voltage, the current should have been 0. And even in the transient network, it starts off in the same way. And this is a single memory block element, right? The inductor has just one memory element. So the next time step it goes to, it is going to look at this value, which was 0 at this voltage. Whether it was transient or steady state, it was the same result that would have occurred. So it has no memory of the switch ever turning on at all. So it will evolve as if it's just a pure steady state network. So this is quite important when we do like closing switch gear for very high current applications. If you know the network impedance to a good enough extent, then you can close your switch for that particular phase in such a way that the voltage is so that the current would start at the 0 even if it was at steady state for that particular voltage, so that you can eliminate this transient, because this transient is quite problematic. The magnitude can get to double of it because this max value is 1. So this plus this could end up having a double voltage, but that in itself is not a problem. This transient is a DC entity. And when DC entities go into transformers, they cause saturation, right, to a very good damaging extent. And that saturation can in turn lead the impedance of the transformer to come down, which in turn can lead more current to flow into the transformer, which will lead further reduction in the impedance, which would lead more current, and it can become a cyclical loop where then your circuit breaker starts to trip along your relays start to trip along your transmission line because of fault diagnosis. All right. So this has quite a bit of application outside of just our machines alone. Okay. So that's the final expression should look like this. Another thing about homework 7, the last question, as long as you make an attempt and you made an honest attempt, like you did some final value theorem and showed some result, at least we can get the results to match when the current is there, but the load torque is not there and your steady state values are correct. That's good enough. I'll ask the TA to give you full points, even if you're not able to figure out how to include the torque component as well into your steady state final value theorem. All right, but still try to do the full work. If possible, I will post the solution once the deadline is over, but I will ask the TA to award full points. So those of you who haven't gotten through all the final answers for this last problem, don't worry too much about it. You won't be penalized much for it. Okay. So today, let's continue. Let's start off with our AC motor. Can somebody tell me what the problems were with the DC motor? Why are we moving towards AC motor? What was the issue with DC motor? Yep,
Brushes wear out.
brushes wear out, perfect. So the brushes wear out, the commutators arc, and the commutators start to short out because graphite forms a nice coating around the commutator, and it can start filling in the mica segments and create long-term shorting. So in a motor, and you have seen this already in the lab motor, when you did the resistance test, you had to rotate the rotor a bunch of times because the brush has completely worn out. And we just operate that motor probably 2 hours every week for the past 5 years, and its brushes are pretty much fully worn out. In case of industrial motors, these would have to be replaced like every couple of 3-4 months. Brushes need to be taken out, replaced, commutators need to be cleaned out and polished, and so on and so forth. So because of this, we cannot have the DC motors are not as efficient and also not as practical for large applications, especially at very high power. So the only option is to take away the brushes in the commutator. Why do we need brushes and commutator in the DC motor in the first place? Because our windings are on the rotor, right? Because we needed rotational isolation while there is electrical contact. That was the problem. Why can't we put our windings on the stator? Why didn't we put our windings on the stator? That would eliminate all the problems that we have. There's another name for commutators. When I introduced the term commutator, I gave another name for it. Does anybody remember that? The mechanical rectifier, right? Because the problem was when we had our windings, every time the rotor rotated, we needed to make sure that the current on the left half of the windings were always in one direction and the current on the right half of the motor windings were always in the other direction. And the only way we could do this is if we had some kind of rectification, because otherwise if we don't have this commutator segment, as the rotor rotated, if the right-hand side currents were going into the page, and when the rotor rotated, the conductor would have gone along with the rotor, and the current would still be going into the page when they come to the left-hand side. So the torque would be pulling upward on the right, torque will be pulling up on the left as well. So it'll just be an expensive pendulum at that point with no applications at all. So when we had our motor, when we had our armature, what we said is we'll put these commutator segments so that when the conductors that are on right, when they come to the left, they would still have current going in the same direction as the conductors previously on the left did. That way we could have a torque that's continuously sustained, right? And the way we could do this in the era when there was no power electronics, or this was pre-AC voltages, right? When we just had batteries which were creating DC voltages, the only option was to put it on the rotor so that you can use the rotor motion itself as a rectification action, right? If we are doing it now, we can put a H bridge and create a voltage that will flip every time back and forth, so we can create the same action. So that was the first problem. We wanted this mechanical commutation to happen. But we no longer need that to happen because in the next 10, 20 years, people figured out how to create AC voltages, right? Around 1830, 1840s itself, people knew how to create AC voltages. You take a magnet, put sinusoidal windings on the stator, you rotate this magnet with whatever mechanical apparatus that you have, and you're going to take AC voltages at the output of the terminal. Pretty straightforward to generate AC voltages, right? So once you have this AC voltage, the voltage automatically changes direction. The current will also change direction. So the commutation action happens on its own. So you can take this winding, put it now on the stator, right? So what we have is, so we have North Pole, South Pole, and we have some stator. Right? We can put some windings on this and pass AC current, AC voltage, and then in turn AC current, so that the current through this is going to flip. Right? It can be pure AC, or you could have some square wave kind of thing, or whatever. So the current is going to be flipping back and forth, so that we have created whatever the rotor is doing in the DC motor. Will this arrangement start to rotate? Whatever I've drawn there, if I start to put AC voltages into the system, will the rotor start to rotate? Take a guess. There are only two options, yes or no. No? Anybody else? Who said no? All right. Sorry, Rachel, you fell into the trap. Why no?
I don't know.
Okay.
It didn't feel right.
Perfect. You have the same intuition as Tesla, nothing to laugh about, right? So something doesn't feel right, it shouldn't rotate. But let's take a little bit of beautiful math that explains why this wouldn't happen. Before we jump into the math, let's just try and get an intuitive feel for what's actually going on. Let's say this voltage is starting to, let's say the current is in the direction going like this, right? So the south field, let's say this pole is south and this pole is north. As the current magnitude starts to increase, the strength of this field, south pole created by this electromagnet is going to increase, while the strength of this north created by this electromagnet is going to increase, right? So if just the strength is alone increasing, what is basically happening is this is getting pulled this side, this is getting pulled this side. So you just get a stretching action on the rotor conductor, on the rotor magnet. You do not get any rotational element to this, right? Now, let's say the magnet, since it's an AC current, the current is going to flip around. So this south is going to become north after half a cycle, and this north is going to become a south after half the cycle, right? So the rotor is a magnet. That direction does not change. So what is now going to happen? This north is going to repel this, so it's going to get compressed. The south is going to repel this. This is also going to get compressed, so it's just getting squeezed. Again, there is no rotational action to it. So now I took a case where the rotor is already starting in the center, but let's say the rotor is aligned in some odd direction, like this. We have some south here, some north here, and then my coil is creating a south here. My coil is creating a north here, right? In this case, what's going to happen? There is going to be a torque component produced because the force is going to be along this direction. You can resolve this into a torque, tangential component and a normal component. And the tangential component is going to pull it, rotate it around. So that this north now aligns with the south and the south aligns with the north. And we'll go back to this initial condition we started with. All right. So irrespective of which position you start your rotor at, you'll end up with this initial position, that initial condition that we considered, the first case that we considered always. And then once it goes to that position, there is no longer rotational element involved in it, right? So this was the problem with putting an AC voltage on the stator. And a lot of people tried starting, once they did the DC motor, with eliminating the problem of commutator was a big headache. And people started investigating how we can eliminate this. And it was about 50 years of investigation before somebody came with the idea that can fix this problem, right? So this is the problem. If you take the winding, put it on the stator, put AC voltage, that just does not solve the problem that we have. Okay. So let's look at what the AC windings on the rotor stator looks like. So again, we are not going to consider the rotor for now, but it is just a magnet with one north pole, one south pole. We are only going to be considering two pole for this lecture. We will do a general N pole later on Friday or the next week. Okay. So the way we are going to wind this. So the way we are going to wind the AC motor, in case of DC motor, when we had a rotor, we had a bunch of slots on the rotor, and all the slots had equal number of conductors. Right, each slot had 10 conductor, 10 conductor, 10 conductor, so on and so forth, with 10 conductor coming out of one side, 180 if it's full pitch, going 180 degree to the other side, going into the page. Right. In case of an AC motor, we are going to be doing it differently. We are going to do what's called a sinusoidal distribution. Sinusoidal distribution. Again, AC motors have many ways of distributing the conductor. There are concentrated winding, there are sinusoidal distribution, but we are going to be looking at the case sinusoidal distribution. If the slot number is small and the pole numbers are large, sinusoidal distribution and concentrated windings don't make much of a difference. But for high power motors, typically you would have sinusoidal distributions, or especially for generators, you'll definitely have sinusoidal distributed winding. So what does it mean? If you look at each of these slots and look at how many conductors are there, And you plot that as a plot. So at around 30 degree, there is, let's say, 3 conductors. After that, so here are 3 conductors. There are 9 conductors here, right? 8 plus 8, yep, 9. And then we have this one, just ignore that one. That was a MATLAB generation error when I rounded it up. So we have here 12 conductors here, 12 again, 9 again, 3 again. When I have conductors going into the page, I'm going to use the negative convention, negative 3, negative 9, negative 12, negative 12, negative 9, and negative 3, right? So this is what I have. So let me plot this as a graph. So from angle 0 to 30 degrees, the number of conductors is about 3. And then from 30 to 60 degrees, the number of conductors is 9. And then from here to here, it's 12. Right? I can repeat the same thing on the other side. And then it goes like this. If I start to put more and more number of slots, this starts to resemble more and more like a sine wave. Right? So this is what I mean by sinusoidal distribution. Okay. So how do we wind this? First, I would put one conductor coming out of the page in that slot, take the same conductor 180 degree apart and take it into the other slot, bring it out. Do this 3 times in that one slot. Once I'm done with it, I'll go to the next slot. So I do this once, do this twice, do this thrice, go to the next slot and do this 9 times out of one, going into the other 9 times. Once I'm done with it, go to the other one. Do this 12 times. Once I'm done, come over to the other one and then do this again and again and again until I'm done and come back to the place where I started, right? Once I end here in a DC motor, the windings closed on themselves. In an AC motor, you'll take it out as 2 separate windings. One being the positive terminal, the other one being the neutral, right? And we'll club all the neutrals together later, but for now, ignore this part. So this is the one we are interested in. Okay, anybody has any question on how we wind this? Okay, so in each of these slots, as you saw there, basically 12 conductors there, 9 conductors here, 3 conductors there. So as I start to put more and more conductors here, the steps start to become finer and finer. As I put more and more slots, I get finer and finer steps, and it starts to become more and more sinusoidal, right? Same thing, and more the number of steps. At some point, it starts to look quite sinusoidal as the step size becomes very, very small. And large power motors, you typically have a whole bunch of slots that makes it looks very good approximate of sine wave. Okay, so right now you're looking at what are the discrete number of slots, but we are going to make a simplifying assumption that on the stator, these conductors are distributed uniformly. So what that means is around 0 degree, the number of conductors is 0. And then at the highest peak, 90 degree, there are a lot of conductors. If there are a lot of conductors, I'm going to represent it by a very big circle. So let's say this is some total of 50 conductors or something like that, right? And here at this point, there is no conductor. In between here to here, the number starts to shrink sinusoidally, right? And you can think of it as a continuous distribution of conductor densities, which we are going to give as NA of theta as some maximum number of conductors times sine of theta. So this is the conductor density. So this is number of conductors per radian. So how do I get the actual number of conductors within any given angle? So let's say I want to get the number of conductors between angle here and here, stretching some angle d theta. Then the number of conductors in that angle is just going to be, let me put the number of conductors as capital N, is going to be equal to the number of conductor density times d theta. Right, so this is the ideal situation. This is what I want the ideal motor to look like, where I can get these kind of sinusoidally nicely distributed set of conductors, which of course would not be feasible because these represent some fractional numbers, right? And in a realistic case, as this d theta goes to 0, that is what I've written here in this expression. Each of these number at any given single point is equal to 0. But if you take over a range of it, it adds up to some finite value, right? So what I'm going to do is, this is the ideal motor that I want to create. But in a practical motor, I have a constraint that there are only finite number of slots that are available to me. So what I'm going to do is, any conductor density that I have here between angle 0 degree to 30 degree for the diagram that I've shown there, I'm going to integrate this over this angle from 0 to 130 degree, that will give me all the conductors that are within this range. And all of that I will take and put it in the one slot that I have available there. Right? How do I put the number of conductors on the slot that comes after it? I figure out the current density from the angle 30 degree to 60 degree, integrate this function from 30 to 60, whatever number I get, I put all of those in the second slot that's available to me. And then I do the same for 60 to 90 degree, figure out what the results comes out to and put all of those in the third slot that's available to me. And I keep repeating this for every slot that I have. If I get a negative number, that means the current conductor is going inside the page. If I get a positive number, that means the conductor is coming out of the page, right? Everybody clear on this part, what I'm doing here? Okay. So let's now figure out what this maximum number of conductors are going to be. So how do I do that? So in that diagram, what is the total number of turns I have? So I have starting with at 0 degree, I have 3 conductors, then I have 9 conductors, then I have 12, and then 12 again, then 9 again, then 3 again. So we have 6, 18, 24, for a total of 48 turns. Right? On the top portion alone, we have 48 conductors. On the top half, here to here, if you sum up all the conductors, we have 48 conductors. And here to here, we have another 48 conductors. So for a total of 96 conductors. So in that example that I have, NC, which is the total number of conductors. In the example that we have, that is equal to 96. And NT is a term that I'm defining, is the total number of turns. That is equal to NC divided by 2. Right? In our case, that comes out to 48. Right? So that's basically saying if I have one conductor coming out of the page and going into a page, those will be 2 conductors, but one single turn. Right? So that's why we have NC divided by 2, 48 here. So if I take this function Na of theta and integrate it from 0 to 180 degree, that must be equal to NC divided by 2, right? Because we have 48 conductors here, 48 conductors here. So this must be equal to NC divided by 2, which is same as NT. So let me do this integral. If you plug in 0 to 180 degree, sum n peak, sine of theta, d theta. Does anybody remember what that integral comes out to? If you integrate the top half of the sine wave alone, you remember from Fourier, that comes out to 2. So this is equal to, 2 times n cap, right? This integral within the sign that comes with 2 must be equal to nt. So which implies our n pi hat is just nt divided by 2. So basically here, this expression, we can rewrite it as Na of theta is nt divided by 2 sine of theta. So let's plug in some values and see if that math makes sense. For those of you doing in-class participation, this is lecture 20 of the 3-lecture series. Okay, so where were we? So the conductor density that I got, Na of theta, is sum nt divided by 2 sine of theta. Let's see if it's making sense for the example that I drew there. So the number of turns in our case was 48. Because number of conductors in 96 divided by 2 is the number of turns, that is 48. Nt divided by 2 times sine of theta, that's our conductor density, which is 24 sine theta. So if I could create somehow a hypothetical motor, this is how I would have distributed the conductor density with all fractional values in between, which makes no sense for a practical motor because conductors can't be fractional or you just cannot continuously distribute them. So in a practical motor, what you do is, given the number of slots, for the conductor at slot 3, the first slot which has 3 conductors, that is basically covering all the conductors distribution from angle at 0 degree to 30 degree, because the slot itself is at an angle of 15 degrees. Right? So everything between here and here, whatever this density function gave, I'll put it inside this one. So how do I get the number of conductors in slot 1? So in slot 1 is just going to be equal to integrate the conductor density from 0 to 30 degree, 24 sine of theta, which is going to be equal to 24 times, again the sign does what the value, sign of it doesn't matter, as you'll see in just a second. So 30 degree, 0 degree, so 24 root 3 by 2 minus 1, right? Because cos of 30 is root 3 by 2, cos of 0 is 1. And this, if you plug it in, that'll come out to approximately negative 3.2, right? So we can't have fractional conductors. So that's just going to be 3 turns, 3 conductors. If I had used this exact thing, there will be conductors going into the page, but I'm just doing conductors coming out of the page, right? Doesn't really matter which one I do. You can look at the bottom, going angle 0 in the other direction or going angle in the clockwise, anti-clockwise direction. That's all the difference is. Okay, so you can do the same thing. Now, if I want to figure out how many conductors are in the second slot, I need to repeat the same thing. So M in slot 2 is just going to be integrate from 30 degree to 60 degree. And whatever value you get, so this is 60, this is 30 degree, you would have root 3 by 2, 1 by 2 flipped around, but and this would come out to be roughly 9 point something. So that's just 9 conductors in that slot. You can do the same for the other slot, it will come out to 12 conductors and so on and so forth. Actually, the last one is quite easy to verify, right? Because there would be 60 degrees to 90 degree, 60 to 90. So the 60 would give you, the 90 would give you 0, the 60 would give you 1 by 2, 24 divided by 2, and that's how we ended up with 12 conductors in the final slot, right? So this is what you're going to do to distribute. Now, if instead of this, I give you more number of slots, you just have to figure out what angle the slot spans, and then all the conductors that have been sinusoidally distributed must be condensed and put into the one single slot that's available to us, right? Everybody clear so far? How we do the distribution? Okay. Right. So let's figure out what the H field is going to look like. So let me draw a bunch of loops and then we'll analyze what I'm doing. So let me draw a loop like this first. Let me say it's H1 here, H1 here. Let me draw a second loop here. So this should be all perpendicular. H2 on this side, H2 on this side. And then the third loop, H3 here, H3 here. And then finally the fourth loop is going to be H4 here, H4 here. Right? What is going to be the H in the ion, assuming that it isn't saturated? Assuming H ion has infinite permeability, what will be the H in the ion?
0.
0, perfect. So the H is only in the air gap, right? So if I go around the loop and integrate the H field for the first red loop, what will be my answer? Integral H dot dl. What is that going to equal to? I hear whispers of 0. Anybody want to confidently say 0? How many of you think it will be 0? How many of you know it will be 0? Very good. So it will be 0 because it doesn't matter what conductor, what the loop drawing is or whatever. Respect to how I choose the loop, integral H dot dl will be equal to the Ni, number of conductors times the current. Right? At this point, all of you should be confident that that's the case. It's a fundamental law of physics. Okay. So if I do that here for this loop, I have H1, let's say the air gap length is some Lg. So H1 Lg plus H1 Lg in the other direction is equal to 0. That means my H1 is going to be equal to 0, right? If I do the same thing for the second loop that I've drawn, integral H dot dl is going to be equal to, again, ignore this one on the top. That's a rounding error in MATLAB. What will that come out to be? For the second orange loop, integral H dot dl?
24i.
24i, thank you. Right? There are 24 set of conductors there are carrying some current I, which we yet don't know what it is. So the value is going to be 24i. I can do the same thing again, H2Lg plus H2Lg is equal to 24i, or my H2 itself is going to be equal to 24 divided by 2 times I divided by Lg, or 12i by Lg. And the rest of it is going to be the same thing for the green loop. It's going to come out to be H3 equal to the total number of conductors is 24 plus 9 plus 9. That was 18. 18 plus 24, that's 42. So 42 I divided by 2 Lg. That's just going to be 24 I by Lg. And then the final loop is going to enclose all the set of conductors, which is 48. So my H4 is going to be equal to 48I divided by 2 Lg, which is going to give me 24I by Lg, right? Everybody clear so far? Okay. Now let me do something weird. So let's say I choose instead a loop like this. Right? Or let me do something even worse. Let's say I choose a loop like this. And let's say I call this some hx on this side, some hx on the return side. Right? So if I go around the loop and integrate h dot dl, what will it be for the black loop that I've chosen? This tiny loop that I've chosen here. What is that integral h dot dl going to be?
0.
0. What would the h then indicate? What is the h going to be for that black loop that I've drawn in the air gap? Anybody think it'll be 0? If you think that's okay, I want to ask you why. Does anybody think it's 0? Anybody think it'll be non-zero? Why will it be non-zero?
Won't the two components cancel out?
Which two components?
The HX going one direction, the HX going, never mind.
Yeah, but I'm drawing a loop. It's not a straight line that I've drawn there.
Yeah.
It's a loop with some height. For the loop that I've chosen with the single loop, can I figure out what the h is going to be? So when we figured out the h in the air gap for armature of a DC motor, I told you that I'll come back to AC motor and ask you the same question that I asked there. So it's exactly the same question that I asked there. For the black loop that I've drawn, can I solve for the h at all? When I drew the red loop, orange loop, green loop, and the blue loop, what was the critical assumption that I made?
Isn't it symmetrical across the,
Brilliant. The symmetry. So the answer Jack gave is basically right. So we took in the previous case perfectly symmetric loops, right? So we had a reason to assume just because if I split it like this, the conductors on the left and the conductors on the right are exactly symmetric. So there is no reason for me to expect h on the magnitude of the h on the left to be any different from the magnitude of h on the right, as long as the loop that I've chosen is symmetric around the axis that we have. But in this case, for the black loop, that is not the case. If I were to split right in the middle, conductors on the top are all having conductors coming out of the page. Conductors on the bottom are all having conductors coming into the page. This is not a symmetric loop in any way. Or even this case that I chose, right? If you see this set of conductors on the left is not the same as the set of conductors on the right. It's completely different. So I can no longer assume that h here is going to be the same as h. So as long as I chose these symmetric loops, I'm making use of the symmetry of the motor. Then I can create these simple loops. With a single loop, I can solve, assuming that h on this side is going to be the h on the other side of the same magnitude. So I can write it down as h1lg plus h1lg and then solve it right away. If I chose some other different loop, I need to have n set of equations, have n set of solutions on the right, and then do the matrix inverse and figure out the answer for each of the h values, right? This is only symmetric motors you can exploit this. And most of the time you will find symmetric motors, right? Anybody any questions? How to get the H field in the air gap? Okay. So if I had to plot this, yep, Hannah.
So based on this drawing, H2 is like enclosing the most conductors, but we have it as the smallest H field.
H1, H2 is the orange, right?
Yeah.
That's enclosing, so H2, I wrote it here. 12I by Lg.
Oh, I see. Okay.
So the orange corresponds to the orange, the green corresponds. Blue is the one that occupies all of the conductors. So the blue would be the highest value. Okay. Any other questions? Yeah.
Is H3 supposed to be 21I over L?
Oh yeah, 21. Thank you. 42 divided by 2 Lg. Okay, so if I were to plot this, how will my H field look like? So if I plotted my current density, that looks sinusoidal. Right, because we are using the sine of theta, or basically the previous diagram that I used. I had, so let me. So if I looked at my conductor in each slot, it has the stepped function. Right, so on and so forth. And if I had a sufficiently large number of slots, or I assume continuous distribution in the theoretical case, it will be sinusoidal. Starting at, it will be basically sine of theta. Some k value, some gain. What will be my h of theta in the air gap? Let's say I'm passing, now we are going to go into the current aspect. Let's say I'm passing some constant current into this winding. All of these current conductors are connected in series, so they all carry the same currents. Right? What is my diagram for my H field going to look like? Is it going to be sine of theta? Is it going to be cos of theta? Okay. So some k value. We'll figure out what the k value is in a little bit, but we'll get the cos of theta function because we go back and look at this diagram. H was maximum at this angle when theta equal to 0. And as I keep going ahead, H starts to fall. It becomes even lower at 90 degree, H was 0. When the conductor is at its maximum, the H field is its minimum, right? So whenever we talk about a magnetic axis for a winding, we will talk about where the H field is its maximum. So when I talk about the magnetic axis of A phase, I would draw it with an equivalent inductor coil along this direction and say this is the magnetic axis, A phase, magnetic axis. What that means is if I had a solenoid and pass some current through it, it is going to have a magnetic field along which the magnetic field of the A phase coil is at its maximum. So going forward, when I don't want to draw all of these coils every time when I draw the motor and analyze the motor, so I'm just going to represent it with the solenoid coil, indicate along the direction where the H field would be maximum for that coil. But that is not the direction where the conductor density is maximum for that phase, right? If I draw this and say this is A phase, the conductor density is actually maximum 90 degree away. What I'm actually indicating is the B field and the H field is going to be maximum along the direction that I've drawn the coil, right? Because if I had a solenoid, the magnetic field will be along the direction of the solenoid's axis of winding, right? Everybody clear for the notation? Okay. So when we have this conductor density, conductor distribution like this, our magnetic field is going to be 90 degree phase shifted with a peak along the zero axis. Okay. So far we have looked at just the A phase alone. And again, if I put more and more conductors, it starts to become smoother and smoother, which is what we want to do. Because the H fields are jagged like this, then our torque is going to have those oscillations. If you try to make it as smooth as possible, the oscillations will disappear out, right? So what next I'm going to do is I'm going to put, in addition to the A phase winding, I'm going to start putting another winding, B phase winding, and then a C phase winding. I'm going to go look at only 3-phase motors. We will analyze 1-phase motor in just a little bit, and then we'll analyze 2-phase motor on Friday. But what is the purpose I want to do 3-phase motor? Why all industrial motors are 3-phase motors? What was the reason? Why don't we do 1-phase or 2-phase? Why don't we do 1-phase? What was the problem? We just saw it last class.
You need 2 conductors and less power delivery per conductor.
Perfect. So the power per conductor is max for 3-phase. Right? It's max for 3-phase. In case of 2-phase, the power per conductor was 2 by 3 P. In case of 1-phase, that was half P. In case of 3-phase, that was 1 P. Right? You had maximum power per conductor. What was the problem with, why don't we go to, so 2-phase has this problem 2 by 3 times P versus 1 times P. What was the other problem with 2-phase? Asymmetry in the conductor. Sorry, Leo, was that what you're going to say? So asymmetry in the conductor. One of the conductor carried √2 times the current, while the other 2 conductor carried 1 current, 1 amp if it were considered. In 3-phase, all 3 conductors carried the same current. There's another big problem with 1-phase system that 2-phase and 3-phase and any number of n-phase doesn't have. Jonah, you gave the answer last time.
Power oscillates.
Power oscillates. So the 1-phase has the other problem that the power starts to oscillate. It is not a constant power. So the torque would oscillate, electromagnetic torque, then the speed would oscillate, and that's why ceiling fans are quite noisy. So we want to go with 3-phase motor that has all the advantages. It has the advantage that the power doesn't oscillate. that any polyphase motor, including two-phase, doesn't oscillate. And it also has the advantage, it has the maximum power per conductor. Any 3, 4, 5, all of them have the same characteristic, with three-phase being the lowest polyphase that has that upper limit that we can get. So we're going to analyze three-phase, but we'll also see one and two-phase as well later. So what we're going to do is, we previously saw the conductor distribution for A-phase alone. How do I represent this? With a coil along the direction where the conductor density is its lowest, because that's where the magnetic field is its maximum. And then the B-phase coil is going to be 120-degree phase shifted. So this is where I'm going to draw my B-phase coil, right? So whatever I had in my A-phase winding, just take it and rotate the stator by 120-degree. You'll get a full set of new windings. Now you put that windings into the rotor, stator structure, right? Where will be the peak of its magnetic field? It will be at 120-degree out. Where will be the peak conductor density for it? 120 plus 90-degree at 210 degrees. That will be where the peak conductor density for the B-phase windings are. Right? Everybody clear what we do with B-phase? Can you tell me what the conductor function would look like? So this was my conductor function for A-phase. How will I draw it for B-phase? Perfect. The answer Thomas gave, basically shifted by 120 degree. Alright, so this will be NB of theta. And the B phase flux would also be shifted by 120 degree. Right, this HA would also be shifted by 120 degree. Something like this, right? I will start exactly at root 3 by 2. Yep, Joe.
So for these other ones, we're saying like theta is relative to that coil position, like theta is 0 at 120 degrees for B.
No, theta is always 0 at 0 degrees. Because if theta was 0 relative, then the B or HP of theta would look same as HA of theta.
Oh, okay, yeah.
Like HA of theta at magnetic axis here, HB of theta at magnetic axis along its own maximum field. So if this was my 0 degree for B phase, then that would have been maximum, but it's not maximum at 0 degree. Right, it's in fact some other lower, it will exactly be negative half or whatever this is, right? Okay, so this was HA of theta. And then you can figure out what C is going to be, another 120 degree phase shifted, you end up with the 3-phase waveform. Okay, so we have A phase, B phase coil put in, C phase is going to be just 120 degree further phase shifted from the B phase, putting it at 240 degree. So the magnetic coil for C phase is going to be here with the magnetic axis along 240 degree. And the peak of this is going to be, what will be the peak of it? Peak conductor density will be at, yep, Leo.
Or plus 90.
Plus 90. So 240 plus 90 at 330 degrees is where the peak conductor density would be at its maximum, or positive maximum. Everybody clear? Okay. So in AC motor, what we're going to do is we're going to put all of these 3-phase winding onto the stator. So you will take a coil, first wind the A phase, right? And it will have this distribution where the A phase conductor is maximum at 90, and then the B phase conductor is maximum at 210 degrees, C phase conductor is maximum current density distribution at 330 degrees. Within each slot, if you do the computation correctly, you would have the same set of total number of conductors. Right? That's the beauty of it. If you look at each of these slots and count the number of conductors, they end up being the same. Because of the way the signs add up. And it will only be the case if we have a sufficiently large number of slots. All right. So let's start analyzing the H field for each of these. So this is our conductor density distribution. And for the A phase alone, if I start passing a DC current into the A phase, my H field is going to be maximum here. So we are going to use vector representation to represent the strength of the H field. Typically, you would want to put it like some color diagram where the color is red here, indicating a very large H field, and color becomes green here at the vertical direction at this point, indicating a very low H field. But that will kind of clutter this whole thing. So I'm using these arrow with the arrow length indicating the strength of the H field at that particular point. If the H field is very large, I use a large arrow. If the H field is very small, the H field is very small, I use an arrow with very small length. Right? So we already figured out what the H field due to an A phase conductors is going to be. It's going to vary with that 0 degree being maximum, at 90 degree going to 0, and go on, so on and so forth. So my vector is very large at 0 degree and nothing present at 90 degree, and continues again and again. Right? Everybody clear so far? Okay. So this is what I've drawn. Whatever diagram we have here, I'm just putting it in a planar fashion. So the way I wrote this diagram here, the convention what we chose here is different from the diagram that I've done there. So when I drew a loop, let's say I drew a loop like this, the diagram that I drew there, I assumed, let's see what I have in the other one. It's 0 degrees. So I assume the convention that going from rotor to stator was positive when we calculated. But in the chart that I've shown there, I'm assuming rotor to stator. In my calculation, I used positive convention. In the chart, I'm using negative convention. That's it. The convention is totally up to you. Yeah, either in the homework or the exam, you can choose whichever convention you want. Going from rotor to stator can be positive or negative, but clearly indicate what you've chosen though. Okay. So the same thing that we have here, except in this case, I've chosen the H field going from rotor to stator is negative. That's why it's starting off with the negative value. So HA of theta is coming out to be some K. We'll calculate what that K is in a second. Times cos of theta, the negative sign to it, right? Very clear? How do I figure out what the K is going to be? Can anybody tell me what the K is going to be? We already calculated it. Yep, John.
Could you just use the maximum field if you already know it's going to be a cosine?
Perfect. It was the maximum value we already calculated, which was right here. 48I by 2LG. Where did that 48 come from? When I enclose this big loop, it's basically all the terms within that loop. Right? So that is NT. NT I divided by 2LG. That is my maximum HG. Right? Everywhere else it varies sinusoidally, starting to reduce. So going back to my chart here, I now have an expression for KT. So this whole thing I can just replace it with negative NT I divided by 2LG times cos of theta, right? Again, this cos of theta comes from the fact that our conductors are distributed sinusoidally. It has nothing to do with the current being sinusoidal. We haven't introduced the sinusoidal current at all. The graph that I've shown here is the spatial distribution of the H field for a constant current going into the motor. So I've pumped a constant, let's say 1 ampere current. Then this is going to be the H field at every single point at the air gap, which is sinusoidally changing. All right, I haven't changed the current at all. Now, what's going to happen to this graph as I start to change the current sinusoidally? This is after all an AC motor. So what is going to happen to this chart plot that I have here? How is it going to vary? Anybody? Let's say this is the chart for the current being 1 ampere. If I cut my current into half ampere, how is this plot going to vary? Magnitude will reduce by half. So if I make the current, let's say this is for I equal to 1 ampere. If I make the current half ampere, this is exactly same thing. That's supposed to be the same jagged step, embedded drawing. Right? This is what it's going to be looking like for I equal to half ampere. So as I keep increasing and reducing the current, this plot is going to say exactly where it is, but it's just going to go up and down, up and down. And when I put negative current, this is going to flip around. So if I put I equal to negative ampere, negative half amp, this is going to flip around. Right? So the time variation is happening in the magnitude as I vary the current, but there is also a spatial variation in the theta and the air gap. So there are two variations happening in the magnetic field and the air gap. One due to the spatial distribution of the current conductors, and another due to the time variation of our current magnitude. Right? Very clear so far? Okay. So going back to this again is the step waveform. If I had more number of slots, it will become smoother and prettier. For the B phase, we are going to have the same H field, just 120-degree phase shifted. I don't want to belabor the point again and again. Same thing, just 120-degree phase shifted. For the C phase, same thing, just 240-degree phase shifted. If I add all the three currents, I have the A phase, HA of theta, HB of theta, and then HC of theta, right? All three H fields in the air gap. In a three-phase motor, can I pass 1 ampere, 1 ampere, 1 ampere into all three phases? So the chart that I've drawn here is assuming that I pass 1 ampere in A phase, 1 ampere in B phase, and 1 ampere in C phase. Is that feasible in a three-phase motor? Olivia, you had a question.
Oh, oh yeah. So for the H of theta, it can be negative cosine or cosine, but you just have to make sure you specify which.
Yep. Yeah, you can choose rotor to stator as positive or stator to rotor as positive. Totally your convention. Depending on which convention you choose, you tell it with a negative sign, right? It wouldn't affect any calculation at all. It wouldn't affect how it rotates, none of it. Yep, Dave.
I was gonna say, answering the question, wouldn't two of them have to be the same sign and then one of them has to be?
Perfect. So some of the three currents have to be zero, right? In a three-phase, three-wire motor. If I had a fourth wire, neutral wire available in the motor, then I can pump 1 ampere, 1 ampere, 1 ampere into the motor and take the 3 ampere coming out of the neutral wire. That's absolutely fine. So let's assume the case is where I have a permanent, AC motor with 4 wires, right? 1 3-phase wires and 1 neutral wire coming out. So I'm somehow able to, not somehow, I'm able to pump 1 ampere, 1 ampere, 1 ampere in all 3 phases and get 3 ampere out. What is going to be the H field in the air gap at any given point? What is going to be the H field in the air gap at any given point? Yep, Olivia.
Maybe 0?
Perfect, it will be 0. Right? Because H field, this is H field due to the A phase. This is H field due to the B phase. Sorry, H field due to the A phase is the red, H field due to the B phase is the green, and H field due to the C phase is the blue. If I take sine of theta plus sine of theta minus 2 pi by 3 plus sine of theta minus 4 pi by 3, that sum is always 0 irrespective of what theta you use. Right? That was one of the characteristics of a 3-phase 3-wire system with balanced loads. You get currents Im sin omega t plus Im sin omega t minus 2 pi by 3 plus Im sin omega t minus 4 pi by 3. Even if you put a neutral wire, there is going to be no current to the neutral wire because the sum of those three by themselves are 0 at every single point in time. That's why we don't need a neutral wire in a balanced 3-phase system. So the same thing happens here. When you have 3-phase signs phase shifted by 120 degree, if you sum them up at any given point, they will all be 0 at every single point. So I can take a sample here. I'll have 3 distinct H fields, right? H field we can superposition as long as the core isn't saturated, and H field is all the behaving like a linear network. Then I can do superposition and sum them up together. H field here would be 0, H field here would sum to 0, H field here would sum to 0, every single point will sum to 0. You can do a quick check right here. The magnitude, let's say, is 5. Magnitude here would be 2.5, 2.5, negative 2.5, negative 2.5. Sum those three, you'll get 0. Or if you do a case where one of them is 0, this would be root 3 by 2 times whatever the magnitude is. This will be root 3 by 2, negative root 3 by 2 times what the other magnitude is. Sum is again 0. Right? So every single point will be 0. Okay. But when I pass currents that are different, that summation will no longer be 0. Right? It doesn't make sense to pass DC current into an AC motor because you're doing nothing. It's as if nothing is happening in the system. It will just create 0 magnetic field. It's of absolutely no purpose. So let's look at what will happen if I start to pass AC currents into each of the phases. And I'm going to shift the AC currents in each of the phase by 120 degree. Right? What will happen if I pass the same AC current into all the 3 phases without phase shift? What is going to be the H field in the air gap? Let's say I pass Im sin omega t in A phase, Im sin omega t in the B phase, no phase shift, Im sin omega t in the C phase. What is going to be the H field in the air gap? At any given time, 0, right? Because the same current, if you take a snapshot at any particular time, all 3 phases have the same current. H field is going to be throughout 0 across space in all position and across time at all times. Okay, so we need to have the phase shift in the current. Okay, so this is the graph of the H field in the air gap when the current is changing. So bottom that I have here, this is current in the A phase as a function of time. This is H in the air gap as a function of theta. So this axis is theta, this axis is time. Okay, so this red dot here, that is basically telling what the current magnitude is at different times in the A phase that I'm pumping. And I already saw if the current is at its maximum, the H field is at its maximum. As the current reduces, the H field starts to collapse. When the current goes to 0, H field is 0 across the space in the air gap. And when the current reverses, H field reverses. Right? So it's just going up and down, up and down. Right? There is a name for this particular kind of wave that isn't moving, but its amplitude alone is changing. What is it called? The idea that it's not moving, what do you call a wave that's not moving?
Standing wave.
A standing wave. So let's see why, if you have a one-phase motor, I made a point that one-phase motors cannot rotate. One-phase permanent magnetic motor at least. Induction motor, there are ways to get it to rotate. Once it rotates, we can keep it rotating. Okay. So we have this waveform that is basically just going up and down in magnitude. Let me write down the equation for this. So HA of theta, and so it varies as a function of both time and as a function of space as well. Right? Across the air gap, it's spatially distributed, sinusoidally distributed. Across time, it's also sinusoidally distributed because the current is varying sinusoidally. So the expression we had is NT I by 2 Lg cos of theta, and I itself is some Im cos omega t times cos of theta divided by 2 Lg. Right? So where else you have seen standing wave? You should have done an experiment in high school that involves standing waves. Anybody remember? All of you did the experiment in your physics lab to estimate the speed of sound, right? How many of you did the experiment? Couple of you. Yeah. Those of you who did the experiment, well, how did you do the experiment? Google did. So it's a very interesting experiment. You take a column, copper column, tube, and fill it with some water. You'll start off with a very high level of water, and then you'll take a tuning fork. Have everybody seen a tuning fork, or am I too old? Most of you. Nowadays, many high schools that I go and visit, they usually just have a phone which creates a monotone. But tuning fork is just a nice mechanical apparatus that if you strike, it'll create a frequency of particular, it'll create a wave, sound wave of particular frequency. We have something similar in electrical network, the tank circuit, LC. You give an impulse voltage to it, it'll create a sinusoidal output, right? An oscillator, the frequency given by 1 by 2 by root LC. So something similar happens here. There is some tension to it, and there is some stiffness, K, and some J, that two interact same as L and C interact in our electrical network. So let's say this is a 440 Hertz signal, and you hit it on this copper column and keep it right next to the mouth of the copper column. You start to create a sound wave, and the sound waves travel through this copper column, and it reflects off this water, and it comes out. There are multiple ways, depending on the water height, it can end up coming as additive or subtractive, and everything in between. So if the water height is between here and here, it will come out to an extent where some of it is adding up. So this will be the case where this wave and this wave are on the exact opposite side. So you'll hear the highest amount of sound at the output. So you'll hear a distinctly very high sound, high pitch with a large amplitude. Here you won't hear any sound at all. In between this column height and this column height, you will see the sound start to diminish as you go from here to here, or if you're going from here to here, you'll start to hear the sound magnitude increase. And you'll take readings of different height of this water column. 2H1. And you'll have some kind of outlet where you can let this water. So you'll start with a very large value of water and start letting out water so that the water column height comes down. And you'll take different readings, and you will take the height where the sound you heard is the maximum. And once you figure that out, you know the frequency, you know this length, you can figure out what this velocity is going to be. So that's the experiment that you do. And this is somewhat quite important to understand, because what this is effectively creating is a standing wave. If you have this pattern, you'll basically get a wave that is has the same characteristic as what we have. So if I plot this along the x-axis with height here, I would get the same waveform going up and down, but these nodes and these anti-nodes, they stay at the same place. It's just the wave collapses, goes back other direction, comes back out. Wave collapses, goes back out, comes back in the other direction. And the frequency at which this will change will be exactly the same as the tuning fork frequency that we chose, 440 Hertz, right? So what this tells us is that if we have this kind of standing wave, we can create it with one forward going wave. So this was the wave that went forward, and this is the wave that got reflected back, right? So whenever you see the standing wave pattern, it should strike back to you to your physics class experiment, what you did, or what you should have done, and kind of decompose it into two components. One that is a forward traveling wave and one that's a reverse traveling wave. So this is what happens in the physics experiment that we do. There is in fact a real world forward traveling wave interacting with a real world reflected backwards traveling wave, which is creating a mathematical standing wave. In our case, we are going to do the opposite. We have a standing wave which is real, but we are going to mathematically decompose it into a forward traveling wave and a reverse traveling wave. Right? That's what we're going to do. We are going to do the reverse of it. In that case, the waves traveling themselves were real. The standing was the mathematical component. Here, this is the standing is the real. We are going to decompose it into two mathematical components. How do we decompose this? Cos A, cos B standing, flashing right there at your face. What do you do? So just use your trig identity. NTIM divided by 2LG. And then this becomes half cos of A plus B omega t plus theta plus cos of omega t minus theta. Let me flip the directions around. Doesn't matter because cos of negative is just cos of the same value, right? What does this show? As time goes on, this variable, this part of the wave is going to move in the airgap in one direction. This part of the wave is going to move in the other direction, right? So we have decomposed the single standing wave into two waves. So let's look at graphically animation, what it looks like. Thank you. Right, so we can decompose this into two waves. Right. So we have, if you look at the black waveform that I have there, as the current changes, the black one is the one that's actually there in the air gap. That's going up and down, up and down. But if you fixate your eye on the purple, don't try to watch both colors are the same. The purple and the orange are the forward traveling wave and the reverse traveling wave. Fixate your eye on one color alone and trace the peak. You'll see it goes in one direction. Fixate your eye on the orange, you'll see it goes in the opposite direction. All right, the same thing happens here as well. If you look at this graph, the black one is the one that's in the actual air gap, which is going up and down, up and down. If you look at this purple, fixate your eye on the dot, one of the peaks of the purple is going in one direction. Fixate your eye on the orange, it's going in the other direction. Right? So we have decomposed it into a wave that is one going forward, one going backward. If you sum those two, take the average, right? We have cos of omega t plus theta minus omega t, theta plus omega t, half of it. That will be exactly the wave that's right in the middle of it. Right? So, everybody clear so far? If I were to put a magnet in the rotor, will it rotate? Thomas, you're telling yes. Which direction would it rotate? Did anybody say no? It won't, right? Because both the reverse traveling wave and the forward traveling wave have the same magnitude. NTI by 2LG divided by half, multiplied by half. That was the magnitude term common outside. Inside the bracket was cos theta plus omega t, cos theta minus omega t. So the cos theta plus omega t will pull the magnet, this H field that's going in this direction will pull the magnet in the anti-clockwise direction. The purple magnetic field will pull the magnet in the, which direction is that? Rotating. The purple one will pull it in the anti-clockwise direction. The orange one will pull it in the clockwise direction. Right? So it's going to end up pulling the magnet equally on both directions, that the magnet is never going to rotate. Right? So this was the problem with a one-phase induction motor, where the one-phase one-phase permanent magnet synchronous motor, where the motor will not start to rotate. Right? So just let's look at a couple of graphs and then we'll go back to this. So we have this waveform. Again, I've just decomposed it so you just see one purple alone, and you can see purple going in one direction, orange going in the other direction. And here you can far more clearly see the waves traveling in the opposite direction. So if I put a magnet, they get pulled in the equal direction on both sides, right? So this was the problem that Tesla had faced when he had to figure out how to make the motor rotate. So a lot of people were trying from 1830s, once DC motor was made, people had recognized a problem that DC motor have these commutators which spark, which wear out, and they couldn't figure out an alternate solution. It somewhat seems obvious that when you put a windings on the stator and put AC voltages, you should get the motor to rotate, but it doesn't rotate. Many people tried it, it doesn't rotate. And Tesla was thinking of this problem for so long that he got extremely sick. And what his doctor said is, you go to the park, take some time off, you should, otherwise you'd likely die if you keep doing this. So he took a break, and Tesla apparently is told that whatever he reads, he can remember it. He had a photographic memory. Most of those are things he told himself, so take it with a grain of salt. But he was a very brilliant guy, though. So he went to walk with his friend back while he was in Budapest, not yet emigrated to US, and he was walking in the park, and he had read this play called Faust by Goethe. Has anybody read the story Faust? Seen a play? Anybody know where that the play is associated with Faustus? Faustian bargain, right? Making the deal with the devil. That phrase comes from the story Faust. So what the story is basically is a guy, he has conquered all knowledge in this world and there is nothing else left to conquer for him. And he becomes very despondent, he becomes dejected and he just wants to kill himself. And but he's also very righteous and so on and so forth. And the devil goes and makes a deal with the god saying that if I can corrupt you, the most righteous man, which is Faust, then you should accept that I am victorious. If not, I'll accept that you are victorious. So he makes this deal with the god, and God believes that there's no way he can corrupt Faust. So he makes this deal, and then devil goes to Faust and makes a very simple proposition. He says that I'll give you knowledge beyond that what you have dreamed. If I do that, you should give me your soul. Right? And Faust immediately jumps onto it because the one thing that he wants is knowledge, and devil gives him what he wanted, and he makes the deal, and then it's a whole nice play about tragedy. If you get a time, sometimes they do it in the theater play here. You should go and take a look at it. It's a beautiful play. But the idea is Tesla saw himself in the position Faust was in. Right? He has done all of this in amazing work, but unfortunately the laws of physics are preventing him from solving the one problem, which is that the motor is not rotating even though he has done everything that needs to be done. Same problem that Faust has. So the poem Faust, there is a beautiful paragraph that's shown there where he basically opines that as the earth, so his own situation, he poetically says that it's same as the sun going across the earth. Right now, its sun is setting here and all life has come to an end. Nobody is going to do anything after it. And sun is going to some other new lands where life is teeming and people are working and new things are to be discovered. And he looks at the birds and he says that if I had wings like the bird, I can chase after the sun and discover new knowledge that are yet to be discovered. So Tesla is in the same problem. He has this motor, he has put these windings, he has these magnetic fields that are standing here and they are not moving. Right? He needs these magnetic fields to move forward. He wants to go forward along with the magnetic field, but the laws of physics are putting a cage around us that he can't fly. As he was reciting this poem from his memory to his friends, apparently this is what passed for recreation back in the day when they didn't have PlayStation. So he was basically reciting the story and then he comes up with a sudden brilliant idea that all I need to do is make this magnetic field go forward and my magnet will go along with it. So he takes a stick in the sand. So he basically draws a coil along this direction and he takes a stick and draws another coil perpendicular to it on the sand. Okay? So as the magnetic field sets in this coil, if you had a current that's phase shifted by 90 degrees, magnetic field will rise in this coil. It's as if you're tracing the sun. As the sun sets in one side, it goes to the other part of the world and rises there. And what will the magnet do? Magnet, like the bird, would trace along the direction of wherever the magnetic field is going. Right? A brilliant idea. Basically, he gave wings to the rotor so that it can fly around and chase the magnet. Okay? So again, this is what he told, and then after 6 years, he emigrated to the US, make this a practical reality, implemented the motor, this two-phase motor, and the rest of his history. But again, before him, he did it. The idea came to him far before anyone else. But before he made it practical, there was a guy called Galileo Ferraris in Italy who actually made the motor before him. But Tesla didn't copy him or anything. It wasn't known that even Galileo Ferraris had invented it. Right? So with that, let's continue with what will happen when we have two more coils on them. We have a couple of more minutes. So let's start putting more coils. So the motor that Tesla created was a two-phase motor. We are going to be looking at three-phase motor today. On Friday, we'll look at two-phase motor, how that behaves. So this is the magnetic field that I have due to a phase coil that I've shown here, the black one going up and down, and then the corresponding forward traveling wave and the reverse traveling wave. Let's look at what the field will look like with the D-phase coils. Right? We have the same thing, but the magnetic field is just phase shifted 120 degree, again going up and down, up and down. This can in turn be resolved into its own positive rotating waveform, negative rotating waveform. And the same thing can be done with C phase as well. Right? Again, it will be 120 degree phase shifted going up and down, up and down. And then it can again be resolved into positive going and negative going. Now, the thing is, if I put all of these three together in the same motor, all three phases, fixate your eye on your, let's see, which one? If you fixate your eye on the purple, you would see that they would all travel, the peak of the purple is the same for all three. But if you fixate your eye on the orange, the peak of the orange for all three are at different angles. Okay, so let me stop it at one particular time so that you can have a better look at it. So again, here also you can see the same thing. If you fixate your eye on the purple, peak of the purple, all three have the same peaks at the purple. But if you fixate your eye on the orange, all three oranges are phase shifted by 120 degree. When you have three sinusoidal waveform phase shifted by 120 degree and you sum them up, what will happen? Three sinusoidal waveform phase shifted, yep, Nathaniel. They all cancel out. So if I had all three phase windings in the motor, the orange waveforms will all cancel out at every single point in space, at every single point in time. The purple will all be additive. Right? So let me stop it at one particular time. Right? You can see all the purples are aligned. All the oranges are exactly 120 degree phase shifted. So when I put this all three windings into the motor at the same time, pass three phase sinusoidally phase shifted current, phase shifted by 120 degree, and have windings spatially phase shifted by 120 degree as well, I get a magnetic field that adds up in the one direction and cancels out in the other direction. That's the same thing you can see here. So same thing, you have three sinusoidally varying in the air gap phase shifted by 120 degree, and each of these peaks are phase shifted by 120 degree as well because the current is phase shifted by 120 degree. And you can think of it as a relay race. So basically the one of the phase is handing the magnet to the other phase, and then that phase hands the magnet back to the other phase, and then other phase. So it will be a never-ending relay cycle where each peak keeps on carrying it forward and forward and forward. When you put all of these three together, the net magnetic field and the air gap is the purple waveform that we have there, right? Which is just the one that keeps on going in the forward direction. And now you put a magnet into the rotor, it will trace along wherever the magnetic field of the peak one is, net magnetic field. All right, each of those are standing waves, but the net magnetic field goes in one direction. Let me just take one more minute to just give you the math of it alone, and then next week we'll look at polyphase motors in general. Those of you have to leave, that's absolutely fine. It's a very simple equation. So this was the equation for A phase. Let me just write it out for B and C, and then cancel this out, and then we are done. So if I had HB of, again, those of you have to leave, please do H of T, that would be NT. Again, if you need to meet me for TARs, we will be meeting in the lab. Theta minus 2 pi by 3. The current is also phase shifted by 120 degree. If it is not, then the 3 will just sum up to 0. So cos of omega t minus 2 pi by 3 times cos of theta minus 2 pi by 3. If I do the same formula, cos of A times cos of B is cos of A plus B plus cos of A minus B divided by 2. NT Im by 2 Lg times 1 by 2. Cos of this plus this is divided by 2 is going to give me theta plus omega t plus 2 pi by 3. This minus this divided by t is going to give me cos of theta minus omega t. 2 pi by 3 minus 2 pi by 3 minus of minus 2 pi by 3 cancel out. So this is what we end up with. If I do the same for C phase, HC of theta, I would have NT by 2 I by Lg Im by Lg times 1 by 2 cos of omega t minus 4 pi by 3 cos of theta minus 4 pi by 3. This term would reduce to half of cos of theta plus omega t minus 8 pi by 3, which is same as minus 2 pi by 3 plus cos of theta minus omega t. Now when I sum up all of this, HC of theta, HB of theta, comma t, HA of theta, comma t, this term plus this term plus this term ends up being 0 because 3 sinusoidally phase shifted signals cancel out. Only things that will add is this and that. So we end up with 3 by 2 times. So what we end up with is 3 by 2 times, right? That half term cancels. So we have NT Im divided by 2 Lg, and we have 3 cos omega t adding up minus theta or theta minus however you want to write it, divided by 2, at 1 by 2 coming from there. So this is the net magnetic field in the air gap. You put a magnet and the magnet is gonna start to rotate. How do I flip the direction of the rotation? So let's say this makes my rotor rotate in the clockwise direction. How do I make the rotor rotate in the anti-clockwise direction?
You change the curve or no?
Change which current? Just swap any two phases. Swap the B phase to C phase and C phase to B phase. What will that happen? Then this will become minus 4 pi by 3, right? And then what will happen? This term would end up becoming, when you add these out, it will be 6 pi by 3, which will make this disappear. But here you will end up with minus 2 pi by 3 here. And here you will end up with minus 4 pi by 3. While this term, right? That's all you need to change. Change A phase and B phase and C phase. The positive sequence would now survive, the negative sequence will cancel out, and you'll end up with theta plus omega t, and the rotor will rotate in the other direction. As simple as that. So in an AC motor, if you have A, B, C, so any sequence, if you connect A phase, B phase, C phase, or BCA or CAB, all of it will rotate in one direction. Let's say this direction. The other three combination, ACB, CBA, and BAC, will all rotate in the opposite direction. Right? With that, we are done. We'll continue on Friday. We have a lab session today. Those of you who are registered for the Wednesday, don't forget. Those of you who are registered for other days, you are welcome to attend on Wednesday. There is a lot of vacancy in the Wednesday session. Oh, you use final value theorem to figure it out. Yeah, those are not just looking at the simulation results and giving the answer.
Got a little sticky. I know.
Oh, you have a delay. It may be easier to just break the sine of omega t plus theta, sine omega t cos theta, plus cos omega t sine theta.
So there's a motor numbers.
So that there is no Laplace
Start
to
over.
it. And don't try to solve the Laplace inverse by hand, just put it in mathematical analysis. Yeah, don't try it by hand.
Put on a,
Yeah.
It's this.
But because all of these are constant. Times omega by square plus omega square plus Vm sin theta times s divided by s square plus omega square.
That makes sense.
Right, and then through this you will multiply that. So you have one term s square plus omega square times 1 by SL plus R. And then s divided by square plus omega square 1 by SL plus R. Just put these two terms alone independently into mathematical and ask for its inverse. It will get the answer.
I do. That's where take a C and MS is the actual.
Interesting.
Oh, I don't know.
Okay.
I don't know about that. So problem 3, I was gonna ask,
I ended up doing the.
It was my-
One block and then doing the one and everything in, but.
Problem is
Sometimes
the.
that's the exact edited chest.
Yeah,
Okay.
but position,
Okay.
but my,
Oh, you can't use the formula that's on the website for version if you're just using just a, are you using a PA controller or just a P controller?
I was using PI.
Oh, okay.
Is that fine? That's what I wasn't sure on because,
Yeah, you can use just a P controller too.
yeah,
That makes the problem very simple. But yeah, you can do a PA
you
controller.
just zero out the, yeah.
Yeah, KI is just zero. But you can't again substitute it into the formula. But your transfer function, right, G of P omega. That would just because your system is now just Kp something, and then it's just an integral, right? That gives you theta. So your G of J omega is just Kp divided by J omega.
Okay,
So if you take the magnitude of this, magnitude of G is just Kp by omega.
okay.
And at the crossover frequency, that magnitude must be 1. So Kp is just omega c. You cannot have a phase margin because the angle of G of J omega in this case,
I mean, if you.
since J is in the denominator, the only angle you can get is negative 90 degrees. That's it. No matter how you adjust omega, you cannot change this angle. Because if there is a real component to it, some real part,
Yeah.
then changing this would change the angle because tan inverse of the imaginary divided by real.
Yeah.
But when the real term is 0, it's tan inverse of imaginary by 0, which is tan inverse of infinity, which is just pi by 2.
Yeah.
It's in the denominator, when you look at the numerator, it becomes minus 90. So the phase margin is always the phase margin. So in this case, you don't have a phase margin control, it's just 90 degree.
Yeah.
Which is absolutely fine. But it solves the problem very easily. Kp is just whatever crossover frequency you choose.
This is what I realized after. Either way, so is it fine?
Other way is also
to
absolutely
do
fine.
the
Yep.
PI control and I ended up getting non-zero values for.
Yeah.
Maybe that's how it should work.
Yep, that's absolutely right.
Okay.
Questions?
Yeah, I got really confused with the end here.
Sorry, I did rush through it.
Yeah, I couldn't.
Yeah, of course. So let's see. Is this part clear?
Yeah,
So we just
I
have
think we
the,
got all of this, but when you went to B phase, I just got lost.
okay. So the B phase equation is same as what we had in the A phase.
Yeah.
It's just that the magnetic field for the B phase is 120 degree phase shifted.
Yeah,
Right? So that's what I'm representing here, theta minus 2 pi by 3. And the current is also phase shifted by 120 degree.
oh, okay.
So I in our B phase is going to be Im cos of omega t minus 2 pi by 3.
Okay. Okay, I think that's what. I was-
Yeah, if the current in the A phase, B phase, C phase were all the same, then the H field in the air gap will be completely zero at all time and all space.
Yeah.
Right, so this also needs to be phase shifted.
Okay,
Alright, so once you have Im cos omega t minus 2 pi by 3, this is what we have. Then you can use cos A cos B formula, cos of A minus A plus B by 2, cos of A minus B by 2. Right? And this is what you end up with.
Yeah, this confused me too.
I guess because this is gonna be a really stupid question, but the HC, the final one,
Yep.
it's just dependent on theta. Is that because,
No, it's, I don't know, I was just getting,
okay,
Yeah, it's a good.
running out of time, so it's. Yeah, it's a function of both time as well as theta.
okay,
Time components come from the current varying in time. The theta components comes from the conductors varying in space.
that makes sense. That makes more sense.
got it.
Right.
Thank you.
Is that clear a question?
No question. I want to make sure I'm interpreting this properly, so I can get beat on it, so.
Hmm?
This is the full.
No, that's the reduced motor model. Because this doesn't have the EMF term, this doesn't have the mechanical system,
Okay.
right? Because we can ignore, I said we can ignore the EMF term because the electrical system is fast,
Okay.
while the mechanical system is slow. But the EMF term appears just as a disturbance because it's slow varying.
Okay, so then. Where do you get the speed? This, the speed and the electromagnetic torque and the low torque is that, so what are you taking out of this model?
Oh, okay, I get you.
You know what I mean?
Yeah. So the system that I have here, this is not the model you use in simulation.
Okay,
This is just a model that we use, reduced order model that we use to design the controller.
okay.
But for simulation, it's the full motor model that you have here.
The full 1 mile plus this.
Yeah, this is the controller that, yeah, just this part alone.
So you'd add the controller for the voltage?
Yep. So put it like a
And then-
subsystem and add it,
And
put
then-
this whole motor in a subsystem and then add the PA controller outside.
Okay, and then for this one, same difference, you add another one.
Yep, another cascaded PA
And
controller,
this is the whole controller again, but then this is like
the reduced order model.
reduced,
Yep.
that you can use calculations for.
Yep.
Okay, what do you mean how can you reduce it in here?
No, you won't reduce it in the simulation. Simulation will have the full model.
Okay, full
For
model,
mathematics, we'll reduce it.
okay, and then,
The way we are able to reduce it, because once we have designed the current controller, we saw that the current controller operates way faster than the mechanical system. So the whole current controller just reduces into a unity gain block,
okay, and then how do you,
just for mathematics of it.
okay. And then how do you get these, like the tau L we know, we have to make this a step instead of a block.
Yep.
right?
Mhm.
And then how do you do the KE and the KT? For
These are all given in the question. I think I said, yeah, on the top.
Oh, KT and the KET equal.
Those are all motor parameters.
Okay, I got you, thank you, I just want to make sure I did it right,
No worries.
thank you.
You have any other question?
I know.